Okay, Assalamualaikum. So for this slide, I will continue and explain about the equivalent circuit of an induction motor. So instead of just referring to this slide, so I will also refer to the other related slide and website to make clear of this part. So after finish on the equivalent circuit, I will proceed to the equation that involve in analyzing the performance of an induction motor. Okay, so let's restart. So in this slide, you can see that the four-phase equivalent circuit of an induction motor is almost similar to the equivalent circuit of a transformer. So the stator side is the primary side of the transformer. So this is the stator side. The rotor side represents the secondary side of the transformer. So this is the rotor side. So the only difference is that on the rotor side, the end point is shorted. So this is the point that we shorted. So it can induce the voltage as well as the rotor current can flow on the rotor side. So now the current start to flow on the rotor side. In this circuit, the magnetizing reactance generates a flux that links with both the stator and the rotor and induces a voltage in both circuits. The magnetic flux rotates with constant amplitude and synchronous speed. Okay, next I will explain on how we can combine the rotor circuit on the side of the stator. So similar concept as a transformer, you have to transfer the impedance value based on the ratio of turns between the stator winding and the rotor winding. But first we have to understand what is the impedance on the rotor side. So I will refer to this website to see the step on combining the circuit between the stator and the rotor. So I want to focus on the rotor side. Okay, on the rotor side, the impedance can be illustrated as this figure. So consists of the induced voltage on the rotor side, so the rotor resistance R2 and the rotor reactance X2. Note that every parameter that depends on frequency will be multiplied by S, which is the slip, which are the source and the reactance. This is due to the fact that because the rotor speed is less than the rotating magnetic field at the stator, so the frequency will also be different. We call as the rotor frequency F2. So to find the current at the rotor side I2, equation number 5 will be applied. Next, equation number 6 show that we can divide the equation with the slip. To understand more, let's understand this statement. The equation number 6 above explains the secondary circuit of an imaginary transformer with a constant voltage ratio and with the same frequency of both sides. This imaginary stationary rotor carries the same current as the actual rotating rotor. So this makes possible to transfer the secondary rotor impedance to the primary stator side. So in simple words, when we divide this equation by slip, so we basically have normalized the frequency on the rotor side equal to the frequency on the stator side without affecting the value of the rotor current. So that's why we can combine the rotor inside the stator side. Next, we look at two different types of equivalent circuit used to analyze the performance of an induction motor. So on the left side is what we call as an actual equivalent circuit, and on the right side is the approximate equivalent circuit. So the difference between these two is the position of the core resistance RC and the magnetizing reactance XM. So due to the fact that the RC and XM are much bigger compared to the stator and rotor resistance and reactance. So the current I0 is much smaller. So we can assume that the stator resistance and reactance are in series with the rotor resistance and reactance by assuming the current flow between these two sides are the same. Now we move to the analysis of equation. Bear in mind that all the analyses are based on first phase approximate equivalent circuit. So you also have to know the properties of Y and delta connection. So for Y connection, basically I line is equal to I phase and V line is equal to Z3 V phase. For delta connection, V line is equal to V phase, I line is equal to Z3 V phase, I phase. So I1, which is the stator phase current, is equal to no load current I0 plus rotor current I2. So to calculate I0 is equal to core current IC plus magnetizing current IM. So IC is equal to V phase divided by RC, and IM is equal to V phase divided by JXM. So to calculate the rotor current I2, the phase voltage will be divided with all the impedance on the left side of the approximate equivalent circuit. So back to the slide. So in this slide, the top figure show an approximate equivalent circuit, and the bottom one show the actual equivalent circuit. Okay, next we move to power and torque in an induction motor. So the power flow diagram of an induction motor is shown below. To understand more, I will refer to this note. I will use this figure to explain on this part. Bear in mind that when we want to calculate the power, so we should consider the total three-phase power of an induction motor. The input power of this motor can be calculated by using either P in is equal to Z3 V line I line cos theta or 3 V phase I phase cos theta. So cos theta is the power factor of the machine. Okay, because the input part of the machine is the electrical power received from the source. Okay, this power need to be transferred to the output port, which is the shaft. But before delivered to the output, we have to consider the losses that occur along the way. When the power travels in the machine, first losses will occur on the stator side, which are the stator iron or stator core loss SIL and stator copper loss SCL. So stator copper loss can be calculated by using equation 3I2 squared R2. Again, the approximate equivalent circuit will be referred to get the equation of each power. So the stator iron loss basically neglected due to the fact that the value of RC is much bigger, so the current flow there IC is so small. After consider losses on the stator side, so the remaining power will travel to the rotor side, as we call as the rotor input power or air gap power. The rotor input power will occur here and here. So the equation for the rotor input power is 3I2 squared R2 over S. R2 and RR is the same, which is the resistance on the rotor side. After this power arrives at the rotor side, next it will face another losses, which is rotor copper loss. So the rotor copper loss will occur here. So the equation is 3I2 squared R2. Then the remaining power after consider the rotocouplers is called as developed mechanical power or PM, also known as induced power or converted power. So the PM mechanical power will occur here. So the equation is 3I2 squared R2 over S 1 minus S. Now the power is basically have been converted from electrical power to mechanical power. So finally, to get output power, we have to consider the rotational losses of the machine. So these losses basically will be given in the question. Derivation of power and torque equation. I think I have explained this part, so you can try to understand this figure together with the equation derived from this on the next slide. Okay, this one. On this slide, I already explained the circuit that consists of P air gap only. So this is P air gap. And then this slide show when we can split the air gap power into rotocoupled loss and mechanical power developed. Induction motor torque and speed characteristic. So how does the torque of an induction motor change as the load changes? How much can an induction motor supply at starting condition? And how much does the speed of an induction motor drop as its shaft load increases? So to answer all questions above, it is necessary to clearly understand the relationship among the motor torque, speed and power. So we can use the equivalent circuit and power flow diagram to derive a general expression for induced torque as a function of a speed. So basic equation for torque is torque equal to power divided by omega. Bear in mind that torque is some kind like force, so it only occurs at the mechanical side. Let's look at this figure. So in this figure, there are 4 locations that we can calculate torque. Torque input, torque mechanical, torque losses, and torque output. So obviously, output torque is equal to P out divided by omega m. Torque losses is equal to mechanical losses P mu divided by omega m. Torque mechanical is equal to P mechanical divided by omega m, but only for torque input is equal to P air gap divided by omega s, because torque input is depend on the force of rotating magnetic field and S. Okay, for your information, torque input is equal to torque mechanical due to the fact that there are no torque losses between torque input and torque mechanical. I just skip this slide because I already explained about the equation of air gap power and the equation to calculate the rotor current I2. For the last part of this note, let's look at the torque speed characteristic. From this figure, it shows that induction motor has 3 modes of operation, which are braking or plugging, motor and generator. Vertical axis represent torque level, either positive torque on the top part of the axis or negative torque on the bottom part of the axis. And horizontal axis represents speed. The bottom part of this figure show the speed in percent of synchronous speed, and also slip as a fraction of synchronous speed. When the speed shows 0%, means that the rotor speed is 0, and when the speed at 100%, it shows that NR is equal to NS. Beyond 100%, NR is more faster than NS, but below 0%, NR should be negative speed. So by using the equation of slip, you can determine the value of slip either positive or negative. Now, let's relook at the properties of these three situations. Case number 1. Omega S and omega M are rotating in the same direction, and omega S is rotating faster than omega M. So this case is the normal operation of the induction machine. So machine operates as a motor. Omega S and omega M are in the same direction, and the slip is positive for motor operation. So in this case, this is the motor region. So torque is always positive. The direction of the rotor speed is the same as a synchronous speed. NR is less than NS, and slip is positive. Case number 2. Omega S and omega M are rotating in the same direction, and omega S is rotating slower than omega M. So if the speed of the machine is increased beyond its synchronous speed by an external prime motor, but still rotated in the same direction as the stator field, the slip will be negative. This region corresponds to the generator operation. For this region, torque is negative. This means that the mechanical power is required to drive the machine, which in turn delivers electric power to the stator terminal. So this is the generator region. So the speed of the rotor is more than the synchronous speed. So torque is negative, as well as the slip. At this region, induction motor works as a generator, delivers electric power to the stator. Case number 3. Omega S and omega M are rotating in different directions. Suppose an induction motor is operating under normal condition at the same value of positive slip in stable region. Now, we interchange any two terminals of the stator. This reverses the direction of the stator rotating field. The rotor speed, omega M, may now be considered as a negative with respect to that of the stator field. For this case, slip is greater than 1, and power loss in the variable resistance is negative. So as you can see here, by this equation, when the slip is more than 1, this resistance will become negative. So indicating that mechanical energy is being converted to electrical energy. Both the power fed from stator and power fed from the rotor are lost as heat in the rotor resistance. This region is called the braking region. So now you can see that this is the region of braking. Okay, so in simple word, at this region, NR is rotated in different direction with respect to NS.